All right, so number 11, page 250. That one when I look at that, I see that everything's in terms of tangents already. So I would typically I start by moving everything to one side if it's all in this terms of the same type of thing. This will give me 3 tangent squared minus 1. That's going to be something that you want to try to factor, but hopefully you realize, and I'm going to erase this quick to let people in, that you can't factor that as a difference of squares the way it stands. So from 3 tangent squared minus 1 equals 0, I would realize that I can't factor that. So I'd go ahead and add 1 to the other side, divide by 3, and solve it using square roots. So when I square root both sides, again, I'm going to erase this here. I wish I could get rid of the waiting room, but the school has forced us to do this now. It's wonderful. I love the waiting room thing. So, okay, I think I have everyone in. So I was at the point on that question where I had tangent squared was equal to 1/3, and then I square root both sides. So when I do that, always remember with square roots, and this is what will get a lot of people in this chapter. You'll lose half of your answers if you don't forget every time you square root, what do you put in front?
Plus or minus.
Plus or minus. So then when I look at the fraction, remember you look at the top and the bottom separately. So I would say I can square root 1. Square root of 1 is just 1. Can't square root 3. I can leave it here because this is something that I see in my chart. So I'm asking myself the question, where is tangent equal to either positive or negative 1/√3? That tells me the plus or minus tells me I'm going to have 4 answers typically. So if I look in my chart, the first place that tangent's equal to 1/√3 happens at, I believe, pi/6. And because of the plus or minus, you're going to have 1 in every quadrant at the pi/6 reference angle. So that is 5 pi/6, 7 pi/6, and 11 pi/6. Okay. For those that are joining, we're starting with homework questions. Right now, we are on 249, 250. Anyone else have anything you want to look at on those 2 pages? 249, 250. Or we're okay on those? Yeah, okay. In that case, let's take a look at page 252, 253. I know 4 has been kind of a fun question for a lot of people. I've had numerous questions about 4. Anyone want to see that one?
Yes, please.
Yeah. Okay. So 4, my first thing on this one, and remember, like, these 2 worksheets were kind of separated into the first one was mostly just factoring and solving with one trig term. And then this second set, this is where we started to bring in the identities and other stuff that we've been looking at. So my first gut instinct on question 4 is, holy cow, there's a bunch of trig identities. I really don't like the fact that I have 3 different trig functions. I have a cosine, a cotangent, and a sine. You can't solve till you get like one of them, unless you can get it down to what we did on that last notes page where it was like sine is equal to cosine. Then you can kind of think through that process, but it's rough till then. So I would go through for, first off, and I was talking to Erin about this one yesterday, if you have fractions in solving, one of my first things to do is to get rid of the fractions. So my first thing that I did here was to take the 1 minus sign and multiply it over to the right-hand side. So I will distribute the 3 to that. You really can't solve well when there's fractions in there. So my first thing is to get rid of those. My second thing would be on the top part of this. The easiest thing to get rid of would be the cotangent. And that should also give me a little bit of, I'm headed in the right direction, because if I take cotangent out and make it cosine over sine, now I'm down to 2 trig terms, and at least they're the same. So that kind of helps me roll in the right direction. And some of the same stuff applies from proofs. Like one of the methods is getting everything in terms of sines and cosines. So this is not a bad thing to do here. But it does put you back into fractions here, where this is cosine squared over sine on the left-hand side. I'm going to erase real quick to admit someone, and then I'll be right back on that one. Okay. Going back to that, if I can. Oops, hang on. I was at the place where I had cosine squared over sine is equal to 3 minus 3 sine. So just like I did on the last one, I don't really want to keep fractions here. So I would then also go ahead and multiply the sine over to the right-hand side and distribute it in. So this gives me cosine squared is equal to 3 sine minus 3 sine squared. Now it's a little bit more obvious there's one thing that doesn't fit. You know, like back in preschool when they say what doesn't belong. One thing doesn't belong here. What is it?
The cosine squared?
The cosine squared. Everything else is in terms of sine. And if I'm looking at like what should I replace, yes, I could replace the sine squared, but I cannot replace that sine right there. That's harder to do. So if my answer, if I'm looking at what I can replace, I can take the cosine squared and make that in terms of sine. Now everything's in terms of sine. Now I can proceed exactly like I would have with the other page. So I would move everything to the left and factor it as a trinomial. So if I add the 3 sine squared to the negative sine squared, it gives me 2 sine squared. I would subtract the 3 sine x, and then I would keep the plus 1. And then I would just factor the trinomial as normal. 2 sine x and sine x. Factors of 1 when it's positive and the 3 is negative have to be -1 and -1. So I'm looking for, once I set my factors equal to 0, where is sine equal to 1/2 and where is sine equal to 1? So walking through those one at a time. Sine is equal to 1/2 for the first time at pi over 6. Sine is also positive 1/2 in the second quadrant, then at 5 pi over 6. Sine would then be negative in quadrants 3 and 4, so I wouldn't include those. And then sine is going to be equal to 1, only one place, and that will be at pi over 2. You'll see that in your chart, but you won't include 3 pi over 2 because it would be negative down there. Okay. That, though, I would say that's a great example of a question. Well, let me back up a step. I hope you would see that as I write quizzes and tests, I don't make everything like the same level. There will be some basic questions that are pretty easy to solve. And then we kind of progress through like medium ones and get to ones that, when I say hard, I don't mean like impossible. I just mean they're kind of harder to do. They take a little bit more work, but they do show me if you really understand what you're doing. That is kind of where I would like max out, not necessarily challenge problem, because there's no real twist to that question. It just takes a lot of algebra, but that's a higher level question right there. You have to replace identities. You have to use a lot of different algebra stuff. You have to get factoring. There's several things that you would have to do to get through that. So that's about as hard as I would make a test question that is not a challenge question, just so you can kind of reference that. Were there any other homework questions that we wanted to go over through 254, number 9?
Could you do number 8, please?
Number 8, yep. My first instinct on number 8 is we don't have the same trig terms right now. So can I replace tangent squared or can I replace secant?
Tangent squared.
Tangent squared, that's one of our Pythagorean identities. So according to our identity sheet, tangent squared can be replaced with what?
Secant squared minus 1.
Okay, secant squared minus 1. Good. Which should be a good sign because now we're all in terms of secants. So once I get here, I'm going to go ahead and distribute. That's going to give me 2 secant squared. I can already tell that this is going to be a trinomial, so I'm going to move that 3 secant to the left by subtracting it. And then finish with the -2 that I would have gotten from distributing. I would then go ahead through and factor this. 2 secant squared is going to be 2 secant and secant. And then the -2, I would have to put the -2 here because it can't go in the first one because of the greatest common factor. And then +1, check. -4 plus 1 adds up to that -3. And then set your factors equal to 0. So I get secant is equal to -1/2, or secant is equal to 2. Remember that it's easier not to solve right here, but it's easier to take this then into the reciprocal. So this means that I'm looking for where is cosine -2 or where is cosine 1/2. Now, there's a problem with one of those. Which one?
-2.
The -2.
-2.
We talked about the parent function only goes cosine 1 and -1. So I've got to eliminate the -2 there. That doesn't mean I have no solution. That means I just get the solutions from this one. So I look at my chart. Cosine's equal to 1/2 at pi/3. Cosine would again be positive around in quadrant 4 at the pi/3 reference angle there, which is 5 pi/3. Okay. Any questions or problems on that?
Can we do 6, please?
On that same page?
On 253. 6.
53. Yep,
Yeah.
absolutely. All right, so question 6, while it's not in terms of the same trig function, all of it, I always kind of check first, like if there's a tangent squared and a tangent, if I move everything to one side, could I take out a greatest common factor before I start replacing things? So that's what I would kind of look at first on that one. I would subtract that entire term to the left-hand side. Tangent squared minus 2 tangent x sine x. So if I check GCF first, that means I'm taking out a tangent, which means I'm left with a tangent minus 2 sine. That's okay right now because I can set this equal to 0. This is still kind of a mess if I set it equal to 0. So I can work with that as well. If it was me right now, I would kind of ignore this guy over here. That one's safe the way it is. And I would probably use some trig identities to work with just that parentheses. So I would change tangent to sine over cosine and get a common denominator by multiplying by cosine over cosine there. Combining that into one fraction would look like this. And then I can take out a GCF again. Now my greatest common factor on that one is sine x, which would leave me 1 minus 2 cosine x over cosine x. What really is this right here?
Tangent.
Tangent.
Tan, right?
So that's another tangent being equal to 0. Do I really have to set tangent equal to 0 over here a second time? No, because I'm going to get the same answers as I did here. So I'm then just worried about this one being equal to 0. So if I make that equal to 0, I get 1 equals 2 cosine x, or cosine is equal to 1/2. So now those two things that I've circled are what I'm worried about. Where is tangent equal to 0? And where is cosine equal to 1/2? You can do this question other ways. This is just kind of how it came to me right now. I'm sure there's other ways to do this one. So tangent is equal to 0. If I look at my chart, tangent is going to be equal to 0 at 0. So where else?
Pi.
Good. And those will be the only two places because 0 goes with pi and then it goes again with 2 pi, but we're not including 2 pi. Then I would say where is cosine 1/2? We just did that one, so I'll quickly just remind you that was pi over 3, 5 pi over 3. Okay. What other homework questions do we have to look at here?
Miss Langer, I got a quick question.
Yeah.
Why don't you include 2 pi? Because like on the key it says that you do.
Oh, because I didn't edit my key.
Oh.
Because if you look at the directions, it does say including 2 pi. That's something I realized I had in there last year, and I was like, oops. So I really need to edit everything and make it just less than 2 pi.
Oh, okay.
Edit my keys as well because I thought that one, I didn't. Which other one?
Number 9.
Number 9. Yep. There's a couple ways to do 9. I would have approached it like I did that last notes question that we did and just say, this is asking me the question, where is tangent equal to cotangent? Since they're reciprocals from each other, I would kind of use my chart to think about that. Like if I go through, let me just write out what the tangent looks like in my chart. Tangent was 0, 1 over root 3, 1, root 3, and undefined in my chart. Those are just my tangents from my chart. So if tangents are those, I get my cotangents by doing the reciprocals. So reciprocal of 0 is undefined. Reciprocal of 1 over root 3 is root 3. Reciprocal of 1 is 1. Reciprocal of root 3 is 1 over root 3. And reciprocal of undefined is 0. So if I'm asking myself the question, where are tangent and cotangent the same? Where does that happen?
At 1.
Right there, 1. Where is that according to our chart?
Pi over 4.
Pi over 4. Yeah. So if tangent and cotangent are both 1 at pi over 4, that's going to happen, not that they're going to equal 1, but that they're going to be equal one other place. Anyone able to think of what that is? Or where it would be? In another quadrant, they're not going to be 1, but they're going to be negative 1.
Two.
It's going to be over here in quadrant 3. Tangent, wait, no, they'll be positive again. Wait,
2.
4 places. I'm a genius. Okay, thinking about that. Yes, in quadrant 2, they'll both be negative 1, right? I'm getting such dead silence because I'm saying stuff wrong. And then in quadrant 3, they'll both be positive again, which will be 5 pi over 4. And in quadrant 4, they'll both be negative again. So 7 pi over 4. So there'll technically be 4 answers to that. You could have also made tangent sine over cosine and cosine over sine, cross multiplied, switched one of the sine squareds or cosine squareds out. But that's kind of messier. So I stuck with just where are they equal to each other. Other questions from homework? Or we're decent at this?
Mm-hmm.
Sounds good. We are going to do our third day today. This is really our last notes. It's using the double angle identities. So we're going to skip the double, like what are they at the beginning because we've already talked about the double angle identities. And we're going to get right on to page.
Miss Lineker?
Yeah.
So I got here a little late. Have you already talked about the quiz?
I can right now. Do you have another place that you got to run to?
Yeah.
Yeah, it's totally fine. So quiz, here's how I designed it. It looks a little bit different than the other quizzes, and it's not just a printout sheet. So it's going to be a lot of, like, you can just write it on a normal sheet of paper, which is totally fine. I have designed it so that it is one question at a time. For those that have been doing great with doing your own work, and I'm not worried about you, I apologize, but this allows me to kind of limit some of the cheating. It locks out each question after you've done it. So just be aware of that. I have, because of that and like the technology of uploading a picture of your work for every single one, I've given up to an hour and a half for this. Not that I feel like it should take you that long, because some of the questions you should run through in like 1 minute. But I just don't want anyone to run out of time because we're taking pictures and uploading and doing that stuff. So there are 10 questions on it. I've created it with like question groups. So like question 1 for you could be different than question 1 for someone else. Again, cheating stuff. So it makes it a little bit easier for me to make sure that everyone's doing their own work. And so there's 9 questions in it that are just normal solving questions. It says in the directions, solve every one in terms of radians, in terms of pi. Anyone know what that means we should not be using for this quiz?
No calculator.
Yes. I mean, if you want to, feel free. You're going to give me all of your answers in terms of decimals. So that's up to you. So all answers are just like we've been practicing in our homework, radians in terms of pi. Feel free to use a chart. I would expect you to, or write one out for yourself at the beginning, however you want to do it. I can't really prevent you from just picking one out of your notebook. And honestly, I think we all have it memorized at this point. So I'm not really that worried about that. And then after that is a challenge problem. Remember the rules for the challenge problem. That's your 10th question. So just translation for us all. Question 10, you get credit just for trying. So that's 10 free points just for trying. So please at least try. But if you can make it through question 10 and you screw up something else, it makes up points for something that you've screwed up elsewhere. So it can help you if you do get through it, and it is possible to get through it. It's not that crazy. So just FYI, you can take it anytime today for second period by 11:59 p.m. I've given it a 90-minute time limit so that you have plenty of time. But do know that if you start at 11 p.m. tonight, it still cuts off at 11:59. So just, awareness of your own time. Second period, it's assigned to you for tomorrow. Same deal. Or not second period, 5th and 6th, B-Day. What am I talking about? So yes, any questions about quiz, format, all of that?
Will it focus more on what we learned last class or the class before that? Or will it be even?
About half and half, I would say. I've tried to make it pretty even that way, that there's some basics, some factoring, some use identities. So I would say about, like, if I'm categorizing it into the 3 things we've talked about, we did the basic ones the first day. I would say there's about 3. Factoring, there's about 3. Using identities, there's about 3. Definitely nothing harder than what I've given you in the homework at all. So if you've done your homework and you get that, you'll be totally fine. The challenge problem ramps it up, but again, you get your 10 points just for trying, and then you get more points back if you need them, if you can solve it. Okay. Other questions? It's also explain your work. So just keep in mind that as you're solving, I want you to write next to it. I didn't set it up since it's not a printout thing, but I do want you to write your steps and then write your work. So things that I would like to see in your explanations, you can be brief about your algebra solving, like get a common denominator, multiply this to the other side, distribute, something like that. I would like to see some mention of reference angles in there, because that's how we're getting a lot of our answers. So like if you get to the place where cosine equals -1/2, your explanation could be, this is not in my chart, but 1/2 is the cosine reference angle, or alpha pi/3. So in quadrants 2 and 3, cosine is negative, or something like that. That is really where I'm gonna like to see the explanation, how you got the radian answers. And that can be however you want. Like I'm using the reference angle language and all that, but that is the place where I'm going to be able to tell if you know how to find the answers using your chart in your unit circle, or if the answers are perhaps coming from elsewhere, if that makes sense. Any clarifying comments about the quiz or questions? No? All right. In that case, we are going to tackle I think I just have a couple questions here on double angle identities. A lot of this will be very, very similar to like what we did last class because it's just other identities. So I'm not going to spend horribly long on this so that you guys have plenty of time for your quiz today. I'm just going to show you a couple tricks to doing these. So for question 1 on page 260, the reason we're going back over this is because the double angle identities help us when we're solving. Right now, the way this stands, when I have a 2x right here and a single x right here, this is unsolvable until everything is in terms of the same trig function or the same x angle. Like those are different angles, 2x and x. And I can't solve this. So then the answer is just like when we did the identities our last lesson, is that which one of those two things can I change? Well, I have 3 options for that one, right? Any guesses as to which one will be the best option for us?
2 cosine squared minus 1.
Cosine squared minus 1. Okay, we're getting used to the fact that I need to use the one that has to do with the problem. And then really from this point, is this any different than what we've been doing? I mean, no, right? I'm just going to move everything to one side and factor. And honestly, I don't even really want to finish this question right now because this is a pretty easy one. Factor, solve, find where cosine equals those values. Anyone feeling a particular need, like I don't know how to finish this question? Okay. The reason I'm skipping that is because there are some double angle ones that are very straightforward like that. Make a good substitution with your cosine 2x and move forward. That's it. There are other ones like 2 that are different, and this is what I want to focus on today. For sine of 2x, do I have options for this one? I only have one double angle identity for sine, right? So let me show you. If I do what I did on the last one and say, hey, I've got a double angle, let me replace this. Anyone see the issue with doing that? Does that help us?
You can't do anything with that.
I can't do anything with that. Okay, so this is where I'm focusing for today. Not every time my double angle identities are going to help me. It's not always a good idea to replace them. To be honest, going back a step, wasn't this a little bit simpler than what we had when we substituted? It really is, okay? Let me just say alternatively, if I had given you, not the 2x, but just this, would you know how to go from here to get your answers? What question is this asking me?
Where is sine equal to 0?
Where is sine equal to 0, right? Well, let's just solve that for a second. Where is sine equal to 0?
0.
Where else?
Pi.
Pi. Okay. Well, here's what we're going to do with this kind of question. Sometimes, if there's just one single double angle identity, and you can use this for a 3x, a 4x, 6x, or any angle you want. We're just going to mentally ignore this for a minute. And we're going to ask ourselves the question, where does sine equal 0? Well, we just got that, right? We know where sine is equal to 0. Well, now let's unignore that and say, here's the problem. These are not my answers for x. These are my answers for what? Those are my answers for 2x. Am I actually done solving for x then?
No, divide them all by 2.
I am going to have to divide all my answers by 2. Okay? So I am going to ignore the 2x. I'm just going to ask myself, where is the sine equal to 0? I'm going to get those answers like I did right here. And then I'm going to divide my answers by 2. Here is one additional problem with doing that. The additional problem is that when we divide our answers by 2, I would like every answer for where this happens between 0 and 2 pi. When I divide by 2, I am losing answers, okay? So here is what you are going to, there's 2 ways to do this. And let me just tell you, the way I was taught is not fun. The way I was taught was to say, what angles could I plug in right here for x that when I multiply by 2, their sign values are 0. So it's this big backwards thinking process. So rather than doing that, I have always just said, if I'm going to divide by 2, I need to go 2 full rotations around the unit circle. 0 and pi were my first rotation around the unit circle. I got where is sine equal to 0. How do I go a second rotation around the unit circle? We did this back in unit 6. Take each of my answers and add to them what?
2 pi.
2 pi. Okay, let's just see what happens. Stick with me for a moment. If I add 2 pi to 0, what do I get?
2 pi.
3 pi.
If I add 2 pi to pi, what do I get?
3 pi.
3 pi.
Okay, now, we had just said to get our answers for x, we're going to divide everything by 2. Let's see what happens when we divide now all 4 of our answers by 2. Are they all going to be between 0 and 2 pi? Well, let's see. 0 divided by 2 is 0. Pi divided by 2 is what?
Pi over 2.
Pi over 2. 2 pi divided by 2.
Pi.
Pi. And 3 pi divided by 2.
3
3
pi.
pi over 2.
Okay, and yes, these are all evenly spaced pi over 2. That is not always going to be true. Someone always asks that at this point. Can I just look at my first 2 answers and add 2 pi to get or add pi over 2 to get the rest of them? No, we can't. It doesn't always work that way. The reason that these are my answers, because if I go back at these answers and I look at them and say, well, sine would equal 0 here and here, but sine doesn't equal 0 at pi over 2 and 3 pi over 2, it's because you are plugging them in here first and multiplying them by 2. So I need to say every radian that when I plug it in there, multiply by 2, gives me 0 out as a sine value. Okay. We all love this so much. This is usually the part that we all hate. Are we like lost in space right now? Or, yeah, we're at the part. I know. This is literally the only thing in this entire unit, in my opinion, that is like big thumbs down. It is not fun. Like I said, I was taught to do this backwards, and that's really not fun to me. And I've tried to teach it that way, and it kind of makes it worse. So if you get the working backwards thing, good. If not, I'm just gonna, like, this is all we're doing now for the rest of class, if that makes sense. So literally from here on out, I'm doing a couple questions on the exact same process we just did. Yep, here we go. Let's do that again. And I'm gonna edit question 2. So on page 261, we're gonna do the same thing. When I see a sign of 2x equal to something, I realize that if I plug in the double angle identity, it's not gonna help me. So I'm gonna kind of skip over the 2x and ask myself the question, where is sine equal to a half? Okay, so let's think about that. In our charts, where is sine equal to a half?
Pi over 6.
Pi over 6, one other place that's gonna happen.
5 pi over 6.
5 pi over 6, good. And those are the only 2 answers for where is sine equal to a half in my first rotation. However, we skipped over this 2x. So these are not my answers for x. These are my answers for 2x. I still have to complete my solving for x. However, I do know, and I remember, that when I divide by 2, I'm essentially losing half my answers. If I divide by 3, I'm only keeping 1/3 of my answers, basically. So if I'm going to show you another one where we divide by 3. So I know that when I divide by 2, I have to think, this is my first rotation around the unit circle. I need to do a second full rotation before I divide by 2. Again, how did we say we do that second rotation?
Add 2 pi.
Add 2 pi to each of my answers. Now I do have to think about when I'm adding 2 pi to each of my answers, in terms of 6, I'm adding what?
12 pi over 6 plus pi over 6.
Yes. So pi over 6 plus 12 pi over 6 gives me what?
13 pi over 6.
13 pi over 6. And 5 pi over 6 plus 12 pi over 6. 17 pi over
17.
Okay. These are still not my final answers for x because my very last step is to do what to all my answers?
Divide by 2.
Divide by 2.
Divide by 2.
Remember fraction rules. When you're dividing by 2, what are you really doing?
Putting
Multiply.
it in the
1 by
denominator.
half.
I'm multiplying by half. I'm putting it on the denominator and multiplying the 6 by 2. Either way you think about it, what it means is the bottoms of these all become 12. So this is pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. In these type of questions, I always do a mental check to make sure all of these answers are between 0 and 2 pi. So I'm always thinking to myself, are all my answers contained in that 0 to 2 pi range? 2 pi in terms of twelfths is the same as 24 over 12. So are all my answers in the correct range? Yes.
Yes.
Okay.
Yes, Annika. So on the ones where we're going to divide by 3, we still add by 2 pi, right?
I'll add 2 pi. You're just going to have 3 rotations. So we're about to do that in just a second.
Oh, that's fun. Okay.
Lots of fun. I kind of like to present all the what ifs so that we answer those kind of questions. I'm going to change question 2 because if you notice, it's the same as the one that we did on the previous page. So we're not going to do that one again. We are going to make this one instead. Let's make this, we haven't done a cosine yet. Let's do that. Cosine of 3x, we'll keep it equal to 0. And this is a good one to do because it's not a cosine double angle identity. If it was a cosine double angle, you could substitute and solve if you wanted, but you could still solve this way. So this is nothing different than what we just did. Let's try it again. We have to usually do this several times in order to get what we're doing. Okay, because of the 3x, we can't really do anything with it. So we're going to ignore the 3x for a minute and ask ourselves the question, where is cosine equal to 0? All right, so
Pi over 2.
where's that going to happen?
Pi over 2.
Pi over 2. Anywhere else that's going to happen?
3
3
pi
pi
over
over
2.
2.
Oh, do we have to go 3 rotations around?
That's exactly what's going to happen. So then this is where you
Ew.
say, well, these aren't my final answers. These are my answers for 3x. And when I divide by 3, rather than only keeping half of my answers when I do that, it's only going to keep 1/3 of my answers. So this is my rotation 1. Because of that 3, I've got to go 2 and a 3rd rotation. Now that does not change what we're adding every time. To go another rotation, you always add 2 pi, always. So 2 pi in terms of halves, what am I really adding though?
4 pi over 2.
4 pi over 2. So to get my second rotation, I say pi over 2 plus 4 pi over 2 is 5 pi over 2. And 3 pi over 2 plus 4 pi over 2 is 7 pi over 2. Now I go one more rotation to get my 3rd rotation for the 3 in front of the x, but I still add 4 pi over 2. So that's what makes it 9 pi over 2 here. And add it to this, 11 pi over 2. To get my absolute final answers, my last step is going to be to do what?
Divide by 3.
Divide by 3. Now, you can do this in 2 steps. Some of them are going to you can start by multiplying 3 on the bottom to all of them, but some of them will reduce. So for example, multiplying 3 on the first one on the bottom makes it pi over 6. But if I do that on the bottom here, that's going to reduce and make pi over 2. If I do it on the next one, it's going to make it 5 pi over 6. The next one is 7 pi over 6. The next one, the 3 and the 9 will reduce, so 3 pi over 2. And the last one will be 11 pi over 6. Mental check, are all of those between 0 and 2 pi?
Mm-hmm.
Yes, they are. Okay. How are we feeling about this process? Slightly better?
Yes.
After practice on your homework, it'll get better than that. This is the rotten kind of part of this. It just is. You just have to practice it, unfortunately. Sorry. But that doesn't mean there's going to be a million of these. So there's that. I would like to, for the sake of argument, just discuss 3, 4, 5 quick. I want to do all of 4 together. 3 and 5, I'm just going to kind of get you started. And if you feel like finishing them, great. What's the issue with 3? First off,
2 functions.
that's bad, right? Is that even one of my double angle identities the way it stands right now?
No.
No. Any ideas as to what I could do to make it look a little bit nicer?
Multiply everything by 2.
Yes, sir. Perfect. Because I recognize that that is pretty close to the sine double angle identity, I also recognize if I multiply everything by 2, it becomes one of my double angle identities. And it makes the right side -1. Then, because that is the same as my double angle identity, I can actually go back to a sine of 2x and use the exact same process we've been doing. Ask yourself the question, where is sine -1 without thinking about the 2x? So where will that happen?
3 pi over 2?
Ma'am, is there any other place that sine will be -1?
No.
No, that's okay. So that's my first rotation. But these are my answers for 2x, so I need to go a second rotation. So add 2 pi in terms of halves to my one answer, that's okay. Gives me 7 pi over 2. And I finish up by dividing all my answers by 2, or multiplying the bottom by 2. So my answers for this are 3 pi over 4, 7 pi over 4. Okay. I really am not going to spend much time on question 5, but 4 is slightly different. Why is that?
Because everything's divided by 2.
Square root.
It's really because of the divided by 2 and the angle. Okay. But I can
Oh.
just like the other ones. Okay. Instead of worrying about that right now, I'm going to ask myself the question, where is sine √3 over 2?
Pi over 3.
Okay, that's going to be pi over 3 in one other place.
2 pi over 3.
Mhm. Now, just like we did before, these are not my answers for x, but this time these are my answers for what?
Over
X
2.
over 2.
X over 2, right? The difference with this is that when you're dividing by 2, you're typically cutting out and keeping answers. Well, this time instead of dividing by 2, what am I going to do?
Put it on the numerator.
I'm going to multiply by 2. If you want to do a second rotation, you can. But what I'm going to tell you is that by multiplying by 2, it's expanding your answers rather than cutting them down. So what may happen on some of these is that you may get answers that when you multiply by 2, it kicks them out of the 2 pi range. It doesn't happen on this particular one, but I'm going to show you in a second one that does. So when I multiply both of my answers by 2, I get 2 pi over 3 and 4 pi over 3. Are both of those in my 0 to 2 pi range?
Yes.
Yes, they are. And these ones, you never have to worry about adding in additional answers because of the multiplying business. But let me just show you, make one small change on that question to show you what I mean by throwing it out of the 0 to 2 pi range. What if that answer was negative instead of positive? Where is sine equal to -√3 over 2?
Seven pi over 6 and 11 pi over, or not.
Close. You're thinking it
4 pi over 3.
4 pi over 3 and
5 pi over 3.
5 pi over 3. But just like before, these aren't our answers for x. These are our answers for x over 2. So what are we going to do to our answers?
Multiply.
Multiply by 2. Well, what happens when I multiply these by 2? What do I get?
They're both outside the 2 pi.
Both of these are larger than 2 pi. So what does that mean for my answers?
No solution.
No solution.
Mm.
Sometimes one of them will get kicked out. Sometimes both of them will get kicked out. But that only happens when you are doing ones like these where you multiply by the 2 rather than the dividing by. It's the difference between what multiplying does, which expands your answers and makes them like spread out more, rather than when you're dividing, it's shrinking your answers down basically. So kind of understanding the difference there on what you're doing helps you know what to do. 5, I don't really want to worry about, other than the fact that when it's like 5, this is just like 1. I can replace the cosine of 2x. What's the best option for that one?
1 minus 2 sine squared.
1 minus 2 sine squared, and then it turns into a normal factoring problem. So double angles can go one of 2 ways. They can go with a replacement, and not all the sine of 2x's you're not going to want to replace. Some of them you will. We'll see one on our homework that way. Just kind of a rule of thumb, if replacing one of them with a double angle identity doesn't help you, go back and see if you can do it like question 2 and question 4, that kind of question. Okay. Double angles will not be on your quiz today. They are not needed. And your homework on this is 2 parts to it. It starts on page 266. I think I did 1 through, I don't remember what I did, 1 through 8 maybe? Could be lying to you. Let me look. Let me pull up your homework. Homework 8 point. Oh, also while I'm in here talking about stuff, I got to the homework and then I'll go back to what I was talking about. It's 266, 1 through 8 and 268, 1 through 11. Upcoming stuff. And I'm gonna need someone to tell me if they can see this or not. I'm gonna show you my Canvas. Here's my Canvas. All right, I have updated Canvas again to start like getting into next week. So next week, Monday is our review day, Monday, Tuesday. I know I don't usually assign a review. I feel like I kind of have to online because otherwise, like, I'm not really going over things. So you'll see under the review, I'm going to do the review video. So any questions we have over this homework, or I'm going to try to have the quizzes graded at least for second period by then. So you can ask questions over that. This review worksheets, it has the answers on it, but I want to see your work. So that's the review that you're going to turn in before the test on Wednesday, Thursday. There's this more trig equations I've put up here. These are harder ones. That doesn't mean that all of them are going to be exactly like the test. Some people like to practice what I would consider the harder level things. Some of them are like really hard, like challenge problem stuff. So if you do go after this more trig equations page, just understand that. Like certain questions on that, maybe about half of them I would consider challenge problems because they're different. But some people like to do that because they're already ready to go on the easier ones. So that's fine. The key to that is there as well. Here's where you're turning in your review worksheets, which is this other one up here. The test will be here. Can someone check? I put the proofs test corrections up here at the top of the module. From our I just put the assignment for that. Can anyone see that or open it?
I'm looking.
With all the restrictions I put on the module, I am not always sure what you can see. And I thought about putting it at the very end because it's not due till next week, but then that means you literally can't submit it till then. So there's that.
Yes, I found it.
And it can open and everything. Okay.
Mm-hmm.
So the proofs test corrections, obviously things are a little bit different here, but I had people seem to indicate that if they didn't score as well on the proofs test as they wanted to, that they would still appreciate the test corrections. So under the test corrections, if I open this up, I have put the corrections template that I've always used there. If you want to print it out, you're also welcome to just do it on a piece of paper and just upload your submission there. If you have 100 on the proofs test, you can upload a smiling picture of your face or a blank paper with a big smiley face or drawing for me or whatever you want to do. Okay? Just upload something, because otherwise I will forget that you did not need to do it, and I will put in a 0 for test corrections, and I don't want to do that. So give me a little smiling picture of your face or something like that. That's not due till next Friday, the 24th. Okay? Questions, comments?
I have a question.
What's up?
If there's a solution, like